Hello, welcome back to the first course in general physics and to the third and last part in the discussion of the mechanics of a rigid body. In this lecture, we will be discussing, or we will continue to discuss, the dynamics of a rigid body, discussing the dynamical quantity, which is torque, that we have touched on by the end of last lecture, and talk about Newton's second law of rotation. Then we will be relating the work done by a torque in rotating an object and the kinetic energy of rotation of that rotating object. We will, after that, define another dynamical quantity for the rotating object, which is the angular momentum. We will state Newton's second law of rotation in its most general form in terms of the angular momentum, rate of change. And we will address the problem of angular momentum of a rigid body rotating about a fixed axis, and look how is that angular momentum quantity expressed in terms of the various variables. And then by the end we will come to the conclusion when we touch on the principle of the conservation of angular momentum. So, as we have discussed in the previous lecture, we mentioned that there is a dynamical quantity called torque that is responsible for generating the rotation in a body as the force acts on the body. And for example, let's consider this case where we have a bar that is fixed at one end and the bar is free to rotate in a plane with respect to this fixed point. And if we consider this assembly of forces acting on the bar at different parts of it, we will notice by experience that, for example, the force F1, which is acting on the bar but is going through the pivot point, the point where the bar is fixed, this force does not lead to either translation nor rotation in the body. Such a force will not produce any motion in the ruler or in the bar, in the rod. It's just like exerting a force on the door at the hinge point where it is attached to the wall. If we exert such a force on the door, it does not turn, it does not move. Similarly, the force F2, for example, which is exerted at the other end of the rod, but it's directed along the rod such that its action, its line of action, is again passing through the pivot point. This force also does not introduce any rotation in the object. It's as if we imagine if we have this a ruler, for example, that's fixed at one end, free to rotate, but if we pull on it by a force like F2, then the ruler does not rotate, does not move at all. However, our experience tells us that if we exert a force like F4, for example, the ruler or the rod will rotate clockwise. If we exert a force like F3, the rod will rotate counterclockwise. And if we exert a force like F5, also the rod will rotate counterclockwise. Now, how does the rotation of the rod respond to the influence of these forces? If we do this very simple experiment, we will realize that the rotation of the rod will depend on the magnitude of the force that we exert on the rod, and also it will depend on how far from the pivot point we apply that force. And this is something that we can also notice by the motion of the door. That's why the doorknob is situated at the farthest end of from the point where the door is attached to the wall, because this way we have a more response of the door to a smaller force, and we can turn it easier than if we move that knob closer, that handle of the door, if we move it closer to the wall. So in general, we realize that this rotation effect under the influence of the force is dependent on the magnitude of the force, but not only on the magnitude of the force, because, for example, the rotation effect, the rotational effect of F1 and F2 is 0, which means that the rotational effect would depend on another factor, and that factor, by experience, is the perpendicular distance between the pivot point and the point where the force is applied. So in order to know the point where the force is applied, we extend the line of action of the force and as a straight line, and then we find the perpendicular distance between the pivot point or the axis of rotation, the point where the axis touches the rod, and between the point where the force is acting. That distance has a great influence on the rotational effect of the body due to the exerted force. And that is why, for example, we see F1 has no rotational effect, because the distance between the line of action of the force F1 and the pivot point or the axis of rotation, which goes through the pivot point O, is 0. And also F2, if we extend the line of action of F2, it goes through the pivot point or the axis of rotation. And again, the distance between this line of action of the force F2 and the pivot point is equal to 0. And thus we realize that the rotational effect depends on that distance as well as on the force itself. Also, we realize that if we are exerting a force on the rod which is pivoted at a point, the farther away the force is, the easier it is to turn that rod. So that means the rotational influence or effect would depend on the distance in a certain fashion, that it increases with increasing the distance. And from simple experimentation, we realize that the torque or the rotational effect is given by the the distance r between the point of pivot or the axis of rotation and between the line of action of the force. If we extend it, this is the perpendicular distance between the axis of rotation and the line of action of the force, and the component of the force which is perpendicular to this distance, F times sine theta. This is the value of this dynamical quantity, the so-called torque, which generates the rotation of the object. If a force is applied on the object, which is fixed at a given point and free to rotate about that point, then the torque or the dynamical quantity that generates the rotation is given by r f sine phi, where phi is the angle. If we look at the point where the force is acting on the object, and r is the distance between the pivot point or the axis of rotation O and between the point of application of the force, and the force is pointing somewhere, then the angle phi is the angle between the position vector r of the point where F is acting and the force itself. That is the torque applied to the object which rotates it. And in a vector form, we can rewrite this torque in the form tau is equal to r cross F. So if we look at the force where it is applied, at which point it is applied, we determine the position of that point with respect to the point of rotation or axis of rotation, and we call that position r, and the force is F as a vector. The cross product of r cross F gives this torque, which is the dynamical variable responsible for the rotation. Thus, the torque as a vector quantity is perpendicular to the plane in which the position r of the point where F is applied and the vector of the force F, where that the plane where those two quantities lie has a normal to it or a perpendicular direction to it, and that perpendicular direction is the direction of the torque. But as we know, each plane has two perpendiculars, one pointing somewhere and the other pointing in opposite direction, 180 degrees. So which is the direction of the torque? Is it the, for example, for a horizontal plane, if the force and the radius vector, the position vector lie on a horizontal plane, then the torque is expected to be perpendicular to that plane, which means up or down. That's the perpendicular to the plane. Which direction it is, we follow the right-hand rule to determine it by simply, as we have discussed previously, we put our fingers along the r direction and turn our fingers towards the F direction, and then we can determine the direction of the product r cross F, which is the direction of the torque. And the magnitude of the torque is given by r times F times sine phi, as we mentioned in the previous slide. Now we are ready to discuss Newton's second law, since, as we know, for the translational motion, we have discussed the relation between the force applied to a particle and the motion of that particle, the acceleration of that particle. And in a similar fashion, we can discuss Newton's second law for rotation, and for simplicity we will focus our attention on the rotation of a rigid body that is the simplest rigid body we can think of, which is simply a point mass of mass m attached to a rigid rod of length r, and that rigid rod is free to rotate about the other end of it, and it can rotate in a plane which is the xy plane as shown in this figure. Now if we apply a force F as shown in the figure, and the force lies in the xy plane, the object or the rigid body is free to rotate in the xy plane, and that means the direction of rotation will be, if we assign the direction as a vector, will be in the z direction, because according to the right hand rule, the object is rotating from x to y counterclockwise in a direction of increase of theta. That means the direction of delta theta will be in the direction of the z axis. Now if we look at this force applied to the particle directly and assume that the angle phi between the direction of the force and between the position vector of the particle itself is phi, then the force F can be resolved into two components. One component is F times cosine phi, which is along the rod, and it's like pulling the particle away from the pivot point, and that does not introduce any effect, does not do anything, because the object is rigid, does not move away. The length of the rod does not increase. And the other component is the perpendicular component to this one, which is F sub t, which is the tangential to the trajectory taken by the object as it is rotating. So F sub t is equal to F magnitude times sine the angle phi. And analyzing this problem, we realize that F sub r, which is the radial component of the force, does not introduce any rotation because its line of action goes through the pivot point O, if we extend it, and thus the distance is 0. The perpendicular distance between the line of action of the force is 0, and the axis of rotation is 0. And F sub t is perpendicular to the position vector, or to the perpendicular distance between the point of action and between the axis of rotation. And thus now we are ready to derive the torque acting on this object. The torque is equal to simply the tangential component of the force, tangential to the arc, of course, F sub t times r, because these two quantities are perpendicular to each other, and the radial component of the force introduces no torque, so that's all the torque that we have. And this quantity can be rewritten in the following fashion. Remember that F sub t is equal to m times the acceleration in that direction, which is a sub t, and the acceleration a sub t is simply alpha times r. So this will give us m times alpha times r, coming from a sub t, times r, which means m times alpha times r square. So the force will influence this rigid body by a torque that is equal to m alpha r square. And now if we rewrite this quantity in terms of angular variables instead of linear variables, we remember that the moment of inertia of this rigid body, which consists of a single particle rotating at a distance r from the rotation axis, its moment of inertia is simply mr square, as we discussed before. So replacing mr square by the moment of inertia with respect to that rotation axis, we obtain the formula tau, the torque acting on this rigid body, simple rigid body, is equal to I, the moment of inertia of that rigid body with respect to that axis of rotation, times alpha, which is its angular acceleration. So this formula, like in Newton's second law, F equals ma, with m replaced by I and a replaced by alpha and F replaced by tau, the torque, it's exactly the same shape. And this tells us that if we know the force acting on this point-like rigid body during its rotation, we can determine its angular acceleration. And from determining its angular acceleration, using the kinematical definitions of the acceleration and the velocity and the position, we can describe fully the rotational motion of that object. Now, this is a special case when the object is acted upon by a single force, a single torque. What if the object is acted upon by different forces, which each one of them is introducing a torque, as we saw in the case of the rod acted upon by 5 different forces. In this case, we add up the torques together, and we say that the summation of these torques acting on that rigid body, as far as these torques are external to the body, because only external forces do introduce rotation, the summation of these torques on the body is equal to the moment of inertia of that body with respect to the rotation axis times its angular acceleration. And we have to remember in this context to take into consideration the sign of the torque, because the torque is a vector quantity. So we will be concerned in adding the torques together in watching whether the specific force is generating a clockwise rotation or a counterclockwise rotation. Whenever we have a counterclockwise rotation, we will put the sign of the torque as positive, and if the force introduces a clockwise rotation in the object, we will use a negative sign for that torque, and then we will add them up together. This equation, although it is applied or derived for a single particle attached to a massless rod, so the whole body has a mass which is a point mass. The rod that we mentioned has 0 mass. Although this equation was derived for that case, but it is more general. It can be applied to the rotation of any rigid body of any form, of any shape, rotating around any axis, as far as we know the moment of inertia of that rigid body with respect to that axis. Now, what about the kinetic energy of rotation and its relation to the work done by the torque when it's applied to the rotating object? We know that if forces are applied introducing motion in the direction of the force, this results in the fact that the force does work on the object to move it, to change its state of motion. And the work done by the object, by the torque on the object, can be calculated. If we calculate it, we will find a statement similar to the statement that we had found with respect to motion in the translational sense, that statement is the work energy theorem, since, as we noticed in deriving the kinetic energy for the body, we have used the translational kinetic energy 1/2 mv squared for each part of the body. So essentially, the rotational kinetic energy that we have derived, which is 1/2 I omega square, is essentially not a new form of energy. It's exactly the same kinetic energy that we were concerned with in discussing the kinetic energy of a single particle moving with a given velocity v. It's the same, but we just write it in terms of angular forms, quantities, instead of with linear quantities. So in exactly a similar fashion as we have discussed before, since the work done by a force is equal to the change in the kinetic energy of the object, and this kinetic energy is derived from the translational kinetic energy, then we can apply these principles and we can conclude that if the force acts on an object, turning it, making it rotate, or vice versa, or alternatively, we can say if the torque acts on the object and introduces work, the work done by the torque or by the force, which is introducing a rotational effect, it's the same. This work is equal to the change in the kinetic energy. This work introduces kinetic energy. It adds up kinetic energy to the system if the change in kinetic energy is positive, and it subtracts, it transfers kinetic energy from the object to somewhere else in case if the kinetic energy is reduced. So that is the way to transfer energy to or from the object. But this, in this case that we are discussing, it is the transfer of rotational energy rather than translational energy. Now, we have mentioned that we can relate the work and energy and kinetic energy. How can we calculate the work? The work, in the usual sense, is calculated by the force, the dot product, the vector dot product between the force and the displacement. And if we remember that a particle in the rotating body is going around a circular path, then the displacement is tangential to that circular path. And if we take a very small element of the displacement, we call it ds. S goes around the arc of the circular path. So ds would be the length, and the direction of it is the tangential direction. So ds, this is the displacement that is a vector displacement that equals to the arc length and is directed tangentially to the circular path. If we multiply this dot product with the force, then the dot product ensures that we pick up the component of the force that is in the direction of ds. That means in the direction of the ds, that means it is the tangential component of the force, as we saw in the previous figure. So dw, the work, the infinitesimal amount of work done as the particle in the body moves a small distance ds, is simply ft, which is the tangential component to the circular path, times the arc length ds. And since the arc length, from the definition of the radial of the angular displacement, since the arc length ds is equal to r times d theta, then the work done during an infinitesimal displacement is equal to ft times r times d theta, the angular displacement d theta during a very short period of time. And f sub t times r is simply the torque acting on the rotating body. So dw is equal to the torque times the displacement d theta. That is the work done during a very short period of time when the rotation takes place through a small angular displacement d theta. That goes to 0 also. In order to evaluate the total work done by the torque, we integrate this quantity from the initial position, angular position of the rotating object to the final position, and we obtain the total work done is equal to the integral from theta initial to theta final of tau, the torque, times d theta. And the relation between the sine of tau and the sine of d theta gives the sign for the work, whether the work done is negative or positive, and this can be obtained from the analysis of the direction of tau with respect to the direction of the change of the angle theta. So the work can be either positive or negative. And now we can introduce the definition of the power. As we mentioned in the context of discussion of the translational motion, sometimes we are interested in the rate of doing work rather than in the magnitude of the work it's done. And in this sense, we are concerned with the quantity which we call the power. It's the rate of change of work. And that power is defined, as we did mention previously, as the derivative of the work with respect to time. It's the rate of change of work done by the torque with respect to time. And dW, as we saw in the previous slide, is simply tau d theta. So dW by dt is simply tau d theta by dt, which is tau times omega. Tau is the torque, and omega is the angular velocity of the object. And this formula reminds us of the formula for the power in the translational case, where we noticed that the power in the translational case is given by the force times the velocity. In that definition, we use the vector form in order to generalize. But if we have motion in one dimension, like this case is a rotation in one dimension, rotation about a single axis. That means it's like rotation in one dimension. So it looks like the formula with the force replaced by the torque and the velocity replaced by the angular velocity. So if we replace the angular variables for the linear variables, we get exactly the same form of the formula. Now we can go on and define another important dynamical variable in the problem of rotation, which is the angular momentum. And we have to remember that the body, as the body rotates, we always are concerned with respect to which axis of rotation, or what is the origin that we choose to define or to calculate these angular variables with respect to. It is very essential to know that. In the same sense, the angular momentum as a dynamical variable is defined with respect to a specified origin, because if we change this origin, the angular momentum changes. It's not fixed for any origin. And that quantity is called small l. That is the angular momentum of the object. And if we consider the object to be a particle, a point-like particle for the time being, for simplicity, we can define the angular momentum of that particle with respect to a given origin as it's passing by that origin with a given distance r from it. If its location with respect to that origin is r, then the angular momentum is defined as r cross p, where r is the position of the particle at a given point in time, and p is its linear momentum given by mv, which gives the final relation: the angular momentum is equal to m times r cross v as vectors. So from this relation, we realize that really the angular momentum does depend on the origin, because it varies with the reference point through the position r, because r is defined relative to the reference point. So if we change r, the angular momentum changes, even though the linear momentum is constant for the object. So the linear momentum, if it's constant, it stays constant. However, the angular momentum depends on the origin with respect to which we measure that dynamical quantity. And this, by analyzing this quantity, by analyzing it using the properties of vector multiplication, is simply the magnitude of the angular momentum is simply m times r times v times sine phi, where phi is the angle between the radius r, or the position vector of the particle, and the direction of its velocity. That's phi. And this can be rewritten in two different alternative forms: m times r perpendicular times v. So either we take mv and we take the component of the position that is perpendicular to the velocity, mr perpendicular times v, or we can take it as mrv perpendicular, meaning we take m times the position, the magnitude of the position vector itself, mr, but we take the perpendicular component of the velocity to that position vector. So we either take the component of the velocity that's perpendicular to the position vector, or we consider the velocity, but we take the perpendicular component of the position vector to it, and that is not a new form. It's just if we multiply v sine theta, it gives us v perpendicular. If we multiply r sine theta, it gives us r perpendicular. So it depends on which one of the two, r or v, is sine theta multiplied by. And it doesn't matter. This is exactly the same statement. And now we can define Newton's second law for rotation, which is in a very similar way and analogous to the case of translational motion. The net external forces, the summation of the net external forces acting on an object, if we consider it to be a point-like object, for example, for simplicity, the net external torques acting on it is simply the rate of change of its angular momentum with respect to time. This is exactly reminiscent, the same form of Newton's second law in the translational case in its most general form, which states that the summation of the external forces acting on the object is equal to the rate of change of its linear momentum. So we just change or switch the linear variables into angular variables, and we get exactly the same form. Also, this can be obtained, this formula can be obtained by looking at the definition of L, the angular momentum, and derive it, and we can get the left-hand side, the torque, by making the derivation right away from the definition of L, the angular momentum L. Now, as usual, for a system of particles, if we have a system, a body consisting of a system of particles, the total angular momentum of the system is simply the summation of the angular momenta of each one of the objects in the system. And as usual, the rate of change of that total angular momentum with respect to time is given by summation of dLi by dt, and that summation gives the summation of the torques, and the torques are categorized into two types: one part of them are torques coming from external agents, which we call tau external, and another part of the torques applied to a given object, the ith object, for example, is the internal torque, which is coming from its interaction with the other objects inside the system itself. But the internal torques cancel in pairs due to the fact that action and reaction between the pairs inside the system exert equal forces and opposite in directions to each other. And since the torque depends on R, if we flip R, or if we flip the force, then the torque gets to be flipped in sign from positive to negative, and the internal torques cancel in pairs inside the system. And so we get the Newton's second law for a system of objects in its most general form. And now we can define the angular momentum of a body rotating about a fixed axis in terms of its angular variables. And the definition is L, the angular momentum of the body rotating about a fixed axis, is simply equals to its moment of inertia, I times omega. And that is exactly the same form of the momentum in the linear case, but we just have to replace the linear variables by the angular variables. The linear case, we remember that it is P equals mv, replacing m by I and v by omega, we get exactly the same form. And this also can be derived from the original definition R cross P of the angular momentum. It can be derived right from there. And finally, we can come to the conservation, the principle of conservation of angular momentum for the system. And we recall Newton's second law in angular form, or for rotation, that is summation of tau x is equal to dl by dt for the system. If we have an isolated system, which means the total external torques acting on it is 0, then dl by dt for the system, which is the rate of change of its angular momentum, is 0, which implies that the angular momentum of the system is constant. If the derivative of a given quantity is 0, that means that quantity is constant with time, which means delta L is equal to 0 between any two times, meaning L, the angular velocity, the angular momentum of the system at any time, would be equal to the angular momentum of the system at any other time. And this is illustrated by this equation. That means L initial is equal to L final at any initial time and at any final time. And this conservation law is the third powerful conservation law after the conservation of energy and the conservation of linear momentum. And it provides us with a nice tool to solve several problems. And it is a vector form that is applied in component form, which means that the angular momentum is conserved only in directions where there is no external torque. In other directions where the external torque is not 0, the angular momentum is not conserved. And at this point, I would like to finish this lecture, and thank you for your attention.